So in section 6.2, we lay more groundwork for dive into exponential and logarithmic functions. We're going to talk about one-to-one and inverse functions. So we've talked about composite and how you can put a function into a function. And now we're going to talk about two special classifications of functions and inverse functions. So first, let's define a one-to-one function. So a function is one-to-one if every element in the range corresponds to only one element of the domain. So I'm going to stop right there. Let's think about what we know. So in order to be a function, we know that each input gives one output. And that's what makes a relationship a function. So to be one-to-one, we're going to add on this extra statement, and each output comes from a single input. Okay, so that makes it even more special. So a reminder that what we've done in the beginning, we took our relations, all the relations between inputs and outputs, and we classified them as either a function or not. So now what we're doing is we're taking this set of functions and we're going to classify them as something called one-to-one or not. Okay, so a one-to-one function means that not only does each input give one output, but each of those outputs can only come from a single input. So in terms of pictures, there are two pictures on the handout. Because I need more room. From a graph point of view, let's deal with a line first. And what we're going to do is we're just going to randomly pick a value for x. So here's an x, and notice that it has a single y that coordinates with it or corresponds to it. But if I take a look at our friend, the parabola, right, then if I take a look at an x value, there's a corresponding y value that goes to it, but there's also another the same y value over here has a different x value. So these two x's correspond to the same y. It's a function, but it's not one-to-one. So this one is one-to-one, while this one is not. And it's because a single output has two different inputs. So we can use something called a horizontal line test to verify that it is a function. And when you do that, what you're doing is you're taking the horizontal line, vertical line makes it a function, but now we're going to use a horizontal line. And if it intersects it only once along its length, it's a one-to-one function. So over here, we can see how it violates that. So, our first example is going to give us three pictures and ask us to identify which one is a function. And if it is a function, is it a one-to-one function? Get those graphs on the board. So this is example one. So the first picture is an absolute value. And as we look at these, you can kind of think about what each of these is. The second, I'm sorry, this is A, this would be B. Trying to be too fast, and it's never very efficient in this. We have a parabola, but this one's turned sideways. We won't actually ever graph these. Those are for the conic sections in pre-calculus. And C looks something like this, and that's a cubic function. So we recognize them for the most part. So this one is a function because it passes the vertical line test. It is not a one-to-one function because it fails the horizontal. So it's a function, but it's not one-to-one. This one's not a function. Function, and that's because it fails the vertical line test. So it's a relation, it's just not a function. So I don't need to go any further with that train of thought. If it's not a function, it can't be a one-to-one function. This guy is definitely a function because it passes the vertical line test. It is also one-to-one because it passes the horizontal line test. So this is what we're going to be dealing with in this section. And for the remainder of the chapter, we're going to be looking at these one-to-one functions. Okay, so that's what a one-to-one function is. Now we're going to talk about the second part of the section, which is the inverse function. So we're going to define it. An inverse function simply takes the results of the element of the range and returns the original element, the domain. So now we're going to take a look at if we have a set of x's and a set of y's, right? What we're doing is we're going to take whatever this x value is and whatever this y value is and interchange them. Okay, so from a point of view, we're going to take a look at a specific function, a line, because they're the easiest to deal with, 2x minus 3. So what the original function would do is you would input an x value, and then what you would do is next multiply by 2, so we're going to say times 2. And then once you have that, you would then subtract 3. So then you would subtract 3, and you'd get an output. So you'd get some y value as your output. So this would be a y, and it's our output. So what the inverse function does is it's going to start over here and use this as its input. It's going to have to undo that subtracting 3, so it's going to add 3. And it's going to have to undo that multiplying by 2, so it's going to divide by 2. And we'll get back over here as its output. So this is the function. This is the inverse down here. So it undoes in order to take this as its input and give you back this as its output. It has to undo each of those processes. So let's do it with a number. So the number we're going to work with is, let's put in a 5. So same function. So we're going to put in a 5. The first thing we're going to do is multiply by 2. So that's going to give me 10. And then I'm going to subtract 3. So following this schema where you're there, and 10 minus 3 would give me 7. So that's the function. That's f of x. Okay, the inverse function is going to take this 7. We're going to add 3. That's going to get me to the 10. And then I'm going to divide by 2, and it's going to get me back to the 5. So we can see that this is undoing what the original function did. And that's what an inverse function does. And you've been dealing with inverse functions long before you dealt with any kind of math. So in order to get dressed and undressed, those are inverse functions of each other. To load and unload the dishwasher, those are inverse functions of each other. So in other words, you load the dishwasher, and then you unload the dishwasher and you back up with the empty dishwasher. So a couple comments about an inverse function. So if f is a one-to-one function with ordered pairs a to b, please catch that. That is important. So it must be one-to-one in order to have an inverse. And that needs to make sense, because if I'm going to put in an input, get an output, and then take that output, put it in this inverse function, you want it to only correspond back to a single number, not to 2, because how would you know what the original input was? So that's why the parabola is not going to work for us, because it's got 2 inputs that give you the same output. So does tell me that the inverse function then, so if the original function does an ordered pair a comma b, so if I have a comma b, then this guy is going to have as its ordered pair b comma a. So this was 5 comma 7. The inverse function would be 7 comma 5. The range of the function will be the domain of the inverse. So the set of inputs is going to be the outputs for the inverse. The outputs for the original will be the inputs for the inverse function. The notation we're going to use is really, really important. There's a lot of background stuff before we can start doing the actual finding of the inverses. So the function, now throwing the eraser around. Never a good sign. So the notation that we use for the inverse function is the function notation, the f. Then you're going to see a little exponent of -1 and then the x. So this is said the inverse of x, or the inverse function, or f inverse is another way to say that. But notice that this little thing up here is not considered to be an exponent. It's not an exponent, even though it's written as one. And it does not mean 1 over f of x. That's what a -1 exponent would mean. It does not mean that. It simply means the inverse function. So, and you know that because it's written in front of the x in parentheses. So it's the inverse of f versus something on the x. So let's find the inverse of a couple of specific functions. So this is example 2. We're going to start off giving you a set of points. So I have -2, -7. I also have -1, 0. I have 0, 1. I have 1, 2. And I also have 2, 9. So this is the original function. This is that. Now notice that it is 1-to-1. Each input is giving me a different output, and each output comes from a different input. In other words, there's no repeated x's and no repeated y's. So I know it's 1-to-1. So then the inverse function is simply going to take each of those points and interchange their inputs and outputs, their x's and y's. The point that was -2, -7 becomes -7, -2. The point that was -1, 0 becomes 0, -1. 0, 1 becomes 1, 0. The next one would be 2, 1, and the last one would be 9, 2. And there's the inverse function. Seems pretty straightforward. Okay, part B says f of x is equal to 1/4 x. Now, in a minute, we're going to have an algebraic process that we'll write the steps down to do this. But for now, we're going to do it by verbally speaking our way through it. So to do this, you would come in, and the first step you would do would be to multiply x by 1/4 or divide it by 4. The next thing you would do would be to subtract 3. So to undo that, what do we need to do? Well, to undo it, instead of subtracting 3, we're going to add 3. And then you come in, and instead of multiplying by 1/4, which is dividing by 4, you would multiply by 4. And then we need our x. So that's not quite right. Let's talk about it and see what we're doing wrong. Okay. So back over here, let's use as our input. Let's try x equals 4, because it's a nice number to work with. So this would take 1/4 times 4 and then subtract 3. So 1/4 of 4 is 1 minus 3 would give me -2. Now, if we've done this right, I can plug the -2 in and get back the 4. Well, if I plug in the -2, 4 times -2 plus 3, that'd be -8 plus 3. That's a -5. I sure did not end up back where I did. And it's because we need some grouping symbols on this. So in order to undo it, you'll remember, since the -3 is the last thing we do, adding 3 needs to be the first thing we do. So I actually need some parentheses around that x plus 3. Now let's see if it works. So again, plugging in the -2. So f inverse of -2 would be 4 times -2 plus 3. Well, -2 plus 3 is 1. 1 times 4 is 4. And sure enough, we get back the original input value, which is what we wanted. So walking ourselves through it verbally worked quite well.